Hello everyone, welcome to lesson 2-4, equations in y equals slope times x form. Let's take a look at the vocabulary. Today we will use words such as direct variation, constant of variation, constant of proportionality. And we will continue to address the question, why are graphs helpful? Let's look at the real world example. Charity. The amount of money David can raise for the Wish Upon a Rainbow Bike-a-thon is shown in the table. Here we have our domain, biking time, and our range, money raised. So our x is for 2 hours, our unit is hours. For 2 hours, we've raised $20. For 4 hours, we've raised $40. And for 6 hours, we've raised $60. So you can already see how much it would be for 1 hour. Notice that for every hour, or for every 2 hours, we're increasing 20. So that means for every hour, we are raising $10, right? So the ratio, to simplify it, or a unit rate, would be 1 hour here to $10 there. Recall that when the ratio of two variable quantities is constant, a proportional relationship exists. This relationship is called a direct variation. The constant ratio is called the constant of variation or constant of proportionality. So let's use this and go back to the example here on the table where we see that when they say a ratio of two variable quantities is constant, a proportional relationship exists. Here we have a proportional relationship, and what we have a direct variation. What we mean is whatever changes here will directly change on this side. Okay, so it's a direct change. For 1 here, I will always have 10 here. That's the rule. 1 here is 10 here. 2 is 20, 4 is 40, and 6 is 60. So 5 would be 50, correct? That means there's a direct variation. And the constant ratio is called the constant of variation or the constant of proportionality. The constant is 1 to 10. That's what it's changing by each time. Every time there's 1 here, there's 10 additional here. Okay, continuing on. Complete the steps below to derive the equation from a direct variation. Remember, we learned about the slope formula in the previous lesson. And slope is actually identified with the variable m. So not s as you would think, but m is the variable for slope. And we practiced in the previous lesson that we have to find the change in y, so y2 minus y1, and the change in x, so we take x2 minus x1, right? And that will give us our slope, right? And if we don't have any change, where you can see here in the next step, we have y minus 0 and x minus 0, we're simply just going to have y over x is our slope. You can change this, the way we align this, and you can see that if I wanted to isolate my y on this side, I simply have to do the opposite operation with the x on the other side. So it on this side it's division, on this side it will become multiplication. So I can write it as y, now that the y is isolated, y equals m times x. And there we have it. This is what we're learning today. This is the equation in y equals slope times x, right? So use the table to find the rate of change, then write an equation in y equals slope times x form to represent the situation. Also, if I can quickly draw your attention to why we subtracted by 0 here, it's because there's no other points given on this graph. We're only given x, y right there, but we're not giving any other point on the line, so we have to work with the only other point that we know is 0, 0, because you can see that the line is proportional, so it's going through 0, 0. Okay? So going back to this question, use the table, which we have here now, to find the rate of change. Then write an equation in y equals slope times x form to represent the situation. So let's identify here. We can see a ratio over here where we have rise over run, correct? So we have our rise over run, and when we replace the variables, I'll replace it with the first one where I have 20 over 2, and simplified is going to be 10 over 1, or just simply 10, right? That is my y. Don't forget, it's y is on the top. It's rise over run. So 10 is my y. So if I were to insert that here, it's not this y, okay? Remember that this 10 over 1 is a ratio, which represents my slope. If I move over 1 on my domain, I will move up 10 on my range. So I move x is 1, y is 10. If I were to graph that, remember I would run 1 to the right and up 10 on the graph. So how can that be represented here? Well, I know that I could write it as y equals, and I'm going to replace the slope with 10 times x, because 10 is my slope. We've already identified that right there, 10 over 1. I don't have to put it over 1 because anything divided by 1 is still 10, or that number. So what am I saying? I'm saying that this means $10 per hour is my rate of change. Okay, so let's make note of the key concept, which is direct variation. In words, a linear relationship is a direct variation when the ratio of y and x, or y to x, is a constant, m, constant slope. We say y varies directly with x, so they change directly. The pattern continues. The symbols, slope equals rise over run, or y over x, or y equals slope times x, where slope is the constant of variation, the constant of change, and slope cannot equal 0. Because if a slope equals 0, then there's no slope. It's just a line. Example, y equals 3 times x. Here we have a slope of 3 over 1, right? And 3 over 1 would mean that we move over 1 and we rise 3. So we move over 1 and we go up by 3. 1, 2, 3. You see? That's where my next dot would be. You could also go the negative route. So if it's negative 3, you move over 1 negative and negative 3. 1, 2, and 3. And you see? There's a dot there. Okay, now let's take a look at example 1. The amount of money Robin earns while babysitting varies directly with the time as shown in the graph. Determine the amount that Robin earns per hour. So here we have the amount of time, and here is the amount of money earned. Time is our domain, and money earned is our range. We see here that after 2 hours, we hit a crossroad where it would be 15. If this is 10, this would be 15, 20, 25, 30, 35, so on. So we can see that in 2 hours, Robin makes $15. 4 hours, Robin makes exactly $30. So based on this amount, we can cut the $15 in half so that we get the 1 hour. And 15 divided by 2 is 7.5. So to determine the amount Robin earns per hour, or the unit rate, find the constant variation. Here's the constant variation. We're going to take 2 points that we find on the, or 2 coordinate or order pairs that we find on our graph. I found this one right here, and then later on there's this one as well, which is 4 and 30, while this one is 2 and 15. Okay, and you can see here 2, 15, and 4 and 30. We can use those to simplify. If we have 15, which is our rise, over our run, which is 2, and we simplify, we have a rise of 7.5 for 1 hour, for the run of 1 hour. So Robin earned $7.50 for each hour she babysits. Okay, let's take a look at the first example. 2 minutes after a skydiver opens his parachute, he has descended 1,900 feet. After 5 minutes, he descended 4,750 feet. If the distance varies directly with the time, at what rate is the skydiver moving? Okay, so the first piece of information that I'm given is that in 2 minutes, the skydiver traveled 1,900 feet, or descended 1,900 feet. That's 1,900, my ride, over my run, which is 2 minutes. Right? If I were to simplify that down to the minute, I would cut that in half, and 1,900 would be cut in half into 950. Okay? That would be 950 feet per minute, as you can see there. So does that check out? Let's say I were to make that into 5 minutes, as we're trying to identify there. Well, 1 times 5 is 5, and 950 times 5 is 4,750, as we see there. So that is, so at what rate is the skydiver moving? The skydiver is moving at 950 feet per minute. Or we could say the skydiver is descending at 950 feet. But if the skydiver is descending, then we have a negative number of 950. Okay, 950 feet per minute. Example 2. A cyclist can ride 3 miles in .25 hour, or a quarter of an hour. Assume that the distance biked in miles, y, varies directly with time in hours, x. So here's our range, and there's our domain. This situation can be represented by y is equal to 12 times x. Graph the equation. How far can the cyclist ride per hour? Now you're probably wondering where we got the 12 from. Well, that's the number of miles in an hour. It's 3 miles in a quarter of an hour. Okay? That's a quarter. So that means if I want to bring this up to a whole hour, I would have to multiply it by 4, which when this gets multiplied by 4, becomes 12. So it's 12 miles per hour is really our unit rate. And that's where we get the 12 from. So y is the total number of miles. So miles biked is our total number of, and x is our total number of hours. So we know we can do 12 per hour, and that's our total number of miles right there. I hope that makes sense now. So now let's look at the table. And here we see that our number of hours is 0. So we input the number of hours. So 12 times 0 is 0. There we go. So 0 hours, 0 miles. And then number of time is 1. So it's 12 miles per hour. At 2 hours, we have 2 times 12 is 24 miles per hour. You see, this is our input and this is our output. That's what we get. So when we input an hour, we get 12. When we input 2 hours, our output is 24 hours. So every hour will be 12. When we input 3 hours, it should be 36. Therefore, the unit rate is the slope of the line, so the cyclist can ride 12 miles per hour. Let's try B. Let's read it together, and after we read it, if you'd like to try it on your own, go ahead. Just pause the video. A grocery store sells 6 oranges for $2. So a unit rate would be how much would be for $1? 3 oranges, correct? Assume that the cost of the oranges varies directly with the number of oranges. This situation can be represented by y being, I'm assuming, our total cost or total number of oranges. Let's see here. What do we have? Oh, we don't even have the domains yet. We have to choose our own domains. So y equals 1/3 x. Graph the equation. What is the cost of orange? Cost per orange. Okay, so let's analyze where we got the 1/3 from. If you look here, okay, we have, this is our slope, right? Y equals m times x. M is the variable used to represent slope. And you know that slope is rise over run, right? So rise over run, y over x, right? Rise over run. And we're saying here that 3 is our run while 1 is our rise. This 1/3 comes from here, the 2 and the 6. This is 1/3. You see that? So $2 is our rise. So the money should be here, cost. See that? And our run, 6, okay, is our number of oranges. So if I just move this up a little bit, I can add the name oranges here at the bottom. Okay, so I have y equals m times x, where m is my slope of 1/3, or $2 for 6 oranges. But it's $1 per orange, rise over run. And that's how I was able to solve what my domain, or what my axis would be. So here we have 1, we rise 1 and run 1. So now we have to try to input a value and create a table. Or we can just simply graph it. We don't have to make a table because we've already been given our slope right there, where we have a run of 3, run 1, 2, 3 to here, and a rise of 1. Notice I have to go all the way here. Okay, so I'll go ahead and put my dot right there. That's my first dot. And then from there I run another 3, 1, 2, 3, and I rise another 1. The 1 is 2 squares here, so I put another dot there. Okay, and then the same thing again. Count, run 1, 2, 3, and rise by a whole other one right there. Okay, and now I can connect the dots, and you can see it goes through 0, 0, and it goes straight line. So that's the answer. That's the slope. But now let's analyze what it means. Over here we have the number of oranges, so I get 1, 2, 3 oranges for $1. So how many do I get for just 1 orange? If we look over here where it's crossing at about 1/3 of $1. Or you could say, if I divide $1 divided by 3 is 0.33, 0.33, and that's how many cents it would cost for 1 orange, about. Okay, let's take a look at our key concept. I feel like it's taking a long time for us to get to this point of the lesson, so we'll have to speed it up a bit. Compare direct variations. You can use tables, graphs, words, or equations to represent and compare proportional relationships. For example, x and y, this is your input and your output, right? So 15 is 3, 20 is 4, 25 is 5, so 30 is 6. It looks here like we always have a 1/5 relationship. See? 5 to 1, 5 to 1, right? Because 3 times 5 is 15, 4 times 5 is 20, 5 times 5 is 25, 6 times 5 is 30. So this is a 5 to 1 ratio, right? And remember, this is your run and this is your rise, so it really should be the other way. It's y over x, as you can see it here. Okay? And there's my relationship, 1 to 5, okay? Where my run is at the bottom and my rise is on the top. And you can see how it's graphed. Okay, we run 5, 1, 2, 3, 4, 5 to there, and we rise 1. And you can go the opposite way and make it negative, where you run backwards 5, and then you drop down 1 by making them both negative, if you want to make the line in the other direction. Okay, here's an example for the next exercise. Please pause the video and read through this example yourself. For the sake of time, I do not want to go through it myself now because it'll make the video too long. So please pause the video and read through it. I'll see you for question C. Pause now. Okay, example C. Let's read it together. Financial literacy. Damon's earnings for 4 weeks from a part-time job are shown in the table. Assume that his earnings vary directly with the number of hours worked. So they have a direct correlation. We have the time worked and the total pay. I would make this my x, my domain, and this my range, how much it ranges by. So if he puts in 15 hours, he gets $112.50. with 12 hours, $90 with 22 hours, 165 with 9 hours. You can see that we're not actually in any kind of order because he's working a different amount of times each time. But we could arrange these in order where we have the 9 as the lowest value and our 22 as the highest value. Let's write it in a way that it's a simple ratio where we have our y over x. And let's just pick one of the values. I'm going to pick the very last one over here, where I have 6750 divided or over 9 hours, right? And when I solve for that and try to get down to 1 unit, I actually get 7.5, so $7.50 per hour. Okay, is that the same for these? Let's just see. If I do it one more time just for the sake of checking, when it gets to 22 hours, I have 165 divided by 22. Let's bring that down to 1. So divide the top by 22 and I get 165 divided by 22. It's again 750. So clearly, when we address the question, which job has the better pay? Explain. Well, this job has the better pay than the $7.50 because 750. Okay, here's my explanation. Therefore, 750 is greater than 735. That's a good explanation using math language. So which job is better? The one he has now. Example 4. Again, for the sake of time, please go ahead and read through the example yourself. Notice that we're using y equals slope times x, which is the direct variation, and we are replacing the variables that we have been given. We've been given an x value and we've been given a y value. A 3-year-old dog is often considered to be 21 human years. We're saying that each dog year is an equivalent of 7 human years. Okay, and that's what we're finding here in order to solve for the slope. So this time we're not being given the slope, we're being given the other values so that we can solve for it. So how do we solve for our slope? Go ahead and read through it. Make sure that you read every single step and analyze the graph. Okay, let's try the question. Okay, question D. A charter bus travels 210 miles in 3.5 hours. Assume the distance traveled is directly proportional to the time traveled. Write and solve a direct variation equation to find how far the bus will travel in 6 hours. Okay, so I'll just start with my y equals mx. And I'm being given that my slope, my ratio or my rate is 210 over 3.5, right? Time is always our domain. Time is always the bottom, and our range is how far. Okay, times x, sorry. And when I simplify that, I actually get y equals 60x. All I did was divide the top divided by the bottom. Okay, so then they want to know how far it'll travel in 6 hours. Remember, time is my x, so I'm going to replace x with time. And now I'll just do it up here so you can see. I have y equals 60 times 6, replacing it with the 6 hours that we have there. And y, which is the number of miles, total number of miles, is 360 miles. Therefore, to answer the question, the charter bus will travel 360 miles in 6 hours. Question E. A monarch butterfly can fly 93 miles in 15 hours. Assume the distance traveled is directly proportional to the time travel. Write and solve a direct variation equation to find how far monarch butterflies will travel in 24 hours. Again, y equals slope times x. Y equals 93 miles over 15 hours times x. When I simplify 93 over 15, I get 6.2. So that's 6.2 miles per hour. And now we have to replace the number of hours, which is x. And they want to know how far it'll travel in 24 hours. So y equals 6.2 times 24. And when I do that, I get, when I get that, I got y equals 148.8 miles. You could say, therefore, the monarch butterfly can travel 148.8 miles, or approximately 149 miles, in 24 hours. That's quite far. Okay, everybody, this is our guided practice right here. It's been a long video. I hope you understood it. Just to make sure that you know what we will be doing, go ahead and read through the guided practice and make sure you feel comfortable with the examples here. If you do not, go back to the video, to these examples, and see if you can review it in order to come to class better prepared. See you then, everyone.